Hi everyone! We're starting our new unit, which is on energy in the cell. And to start us off, I have a question for you. How can this right here is a picture of your muscle cells. So the question is, how can these teeny tiny little muscle cells do something like this? Clearly, your cells are doing a lot of work for you to lift this person to lift so much weight. So what do your cells need to do this? Clearly, they need a lot of energy. But the question is, what is energy? And how do your cells use energy? How do they obtain energy? And when we get to the nitty-gritty details of all the chemistry behind the macroscopic biology. To start us off, energy is defined as the capacity to do work and to cause change. And if you're taking physics, you're probably going a lot more in depth in what energy really means. But there are two major forms of energy that we will be focusing on in this class. Number one is kinetic energy, which is the energy of motion. And the second one is potential energy, which is energy that an object possesses from either its location or the kind of structure that it has. And we're going to be focusing on one specific example of kinetic energy and one specific example of potential energy. So for kinetic energy, it's really a measure of how fast molecules are moving. And what I want you guys to know is thermal energy is specifically the kinetic energy associated with the random movement of those molecules. And so if you look at this picture, clearly this box right here has higher kinetic energy and thus higher thermal energy because the molecules are moving on really fast. And you can see right here, the steam that's rising is because these molecules have gained so much energy that they've actually been released as a gas. In terms of potential energy, you probably are familiar with more potential energy as you move higher up in space, right? You have more potential energy as you can drop down. But in terms of biology, what you want to know is that potential energy is actually stored in bonds. And you can see that as chemical potential energy. So in the same way that this person standing on the top of this cliff has a lot of potential energy, stored inside these bonds between atoms is a lot of potential chemical energy. So thermodynamics is actually the study of these different kinds of energy transformations. And in biology, we're particularly concerned with this because we want to understand how organisms can exchange energy with the environment. How does it take in energy? How does it change the energy it takes in? How does it release energy? Something important to note is that organisms are considered open systems, which means that they can exchange both matter and energy with the environment. It can do both things. So there are two major laws of thermodynamics that we will be focusing on in this class. The first law is that energy cannot be created or destroyed. So it'll just change its form, but you can't artificially create energy and you can't destroy energy. At the same time, the second law of thermodynamics means that whenever there is an energy transfer, it overall increases the disorder or randomness in the universe. What that means is that even though all energy is being converted, it's not 100% efficient. So some of that energy that's converted is kind of lost as heat. So it's still there, but it's in an unusable form of energy. And that heat or randomness, that disorder of the molecules which we can no longer use, is called entropy. Right here is an example. This is cellular respiration, and you can see that you have your starting materials, glucose and oxygen, and as it gets converted into carbon dioxide and water, there's some energy that's released as heat, and that's just, it increases the entropy of the universe, increases the randomness, it's unusable, but some of that energy that can be used to create ATP, which is a usable form of energy. Okay, so in terms of chemical reactions, there's two major types of chemical reactions that we will be focusing on. One of them is exergonic reactions, and the other one is endergonic reactions. Exergonic reactions are chemical reactions that release a lot of energy. This is when the bonds in the reactants have a lot of higher potential energy than the bonds in the products. And so when the reaction occurs, that excess energy that's stored in the reactants gets released. A great example of this would be cellular respiration, where you start off with a sugar molecule that has really high potential energy, and then over time, when the reaction occurs, it kind of gets broken down to smaller molecules like CO2 and water. And in that process, a lot of energy is released in the form, and that energy can be converted into the form of ATP. This right here is a great diagram that just shows that your reactants start off with a lot higher potential energy, and as it moves down to the products, this excess energy is released. And this is just a chemical diagram suggesting the same thing. You can see the reactants here and then the products. This is for cellular respiration. Endergonic reactions is the exact opposite process, where your reactants start off with less energy and you have to put in energy from the environment to create products that have higher potential energy. Right, this is what it just says. Photosynthesis is a really good example of this, where you're starting off with just CO2 and you're trying to create a much higher complex molecule like sugar, and you need energy from the sun to do that. This right here is just a chemical diagram that shows that same thing. This right here, the difference between reactants and products, is the amount of energy you need to put into the system in order to create the products. So in your body, in all living systems, both things are happening, exergonic and endergonic reactions. And the combination of both of those things is called your metabolism. Specifically, a metabolic pathway is just a series of reactions where you're either breaking things down or building things up. Something very clever that your body can do is it actually couples exergonic and endergonic reactions so that the energy released from an exergonic reaction can actually be used directly to fuel an endergonic reaction. And that process is called energy coupling. Okay, so the major molecule that we're going to be using to generate energy is ATP, which stands for adenine triphosphate. And you can see that the major parts are there. There's 3 phosphate groups, there's a ribose sugar, and there's an adenine group. Yeah, adenosine triphosphate. This is the energy currency of your cells. And the way that it stores energy is that those 3 phosphate heads are very negatively charged and kind of crammed together. And so when you're putting 3 negative things very close together, it's like it's very unstable, and it makes them like a spring. It's like ready to pop off and just shoot off its energy. So those bonds are easily broken between the phosphate heads. This right here, I'm going to just show you guys a picture of what happens. Here's your ATP. And then when you add water for hydrolysis, it breaks this bond between the 2 phosphate groups. And when you break that bond, a lot of energy is going to be released. So the way that ATP transfers this energy that it releases to other reactions to fuel them, you can actually attach that phosphate group that just popped off and attach it to a molecule. That process is called phosphorylation, and that's something that we've seen in active transport, right? When you phosphorylate another molecule, you attach that phosphate group to that molecule. That kind of gives that molecule the ATP's energy, and it allows that new molecule to do things. So for example, we talked about active transport where you can phosphorylate that protein, and it allows the protein to change shape. So phosphorylating that active transport protein can give it the energy to change its shape and pop the solute off onto the other side. Something important about ATP is that it's a renewable source of energy. So that means that it's very easily regenerated. You could just really put on that phosphate group right back onto the ADP, and then it'll form ATP. This right here is just the cycle that shows ATP. You can see where if you put in energy into the ADP, you can reform it with the phosphate group and it forms ATP. And then you can easily hydrolyze it and break off that phosphate group, and then it gives off energy for reactions. Thanks so much for watching. We will continue this later.